Good morning, everyone. Welcome to our 6th annual UK conference. Very happy that you're here. Mark and I have been working for the past 5 months getting this program put together, and I think we're really excited, and I hope you guys are excited about what you're going to see over the next 2 days. We couldn't, of course, do this without our sponsors, so thank you DDN, OCF, Storage, VAST, and Hammerspace for being here. We hope that everyone goes and visits their booths in the breakout room that we've got all set up for our breaks and for our lunch. So they've got their tables all put together and they're willing to and ready to talk to you guys. So give them a look-see. So what's, if you don't know about the HPC Advisory Council, just a really short overview of what we do. We've been, around for about 17 years. And we have about 450 members. The goal here is to be able to provide an open platform to be able to showcase all the goods and greats about HPC and, some learning lessons. When we do these learning lessons, they're usually in a form of best practices and documents that can help people who aren't really familiar with HPC kind of get started, and we do that in a number of ways. One of those is the Cluster Center. So we have a center that's based in Santa Clara, California. It ranges in systems between 5 and 10 any time in the given year. Usually we're taking things out, bringing in new stuff. We try to have the latest and greatest technologies that are available. Sometimes we're lucky enough to get some of those new processors and accelerators before anyone else. So we're able to quickly get things moving, develop some best practices, things that we've done to optimize to be able to get better performance, and we do those benchmarking activities and post them online for everyone to be able to see. And you can access them too, so including students that may be here. If they have a research project they want to work on, they don't have those compute cycles available in their university, they can come to us and get some loaner time and check out how their code is running on a variety of different systems. So it's those best practices that we've added, at least in this year. As you can see there with all the blue boxes, we have a lot of applications that we kind of push through. As we get in new equipment, we kind of recycle, show the latest and greatest. So we have some Grace Hopper systems in now, so we're just in the process of benchmarking some of those. So OpenFoam and GrowMax, I believe, yeah, they at least have Grace, or they have GH200s in there, as well as NDR InfiniBand. So as we're getting into the first half of next year, we're hoping that we're going to get some Grace Blackwell and some XDR, some Quantum X800 800 gig InfiniBand products. So, and we'll do another round again of all these applications. So in terms of student learning, we do a lot of activity. Some are with the ISC Student Cluster Competition. You'll hear from EPCC tomorrow about their activities with the Student Cluster Competition. They've been involved probably in the past 10 years, having different teams come in, and they've seen some success. And what's even better is how those students have taken those learnings and be able to apply them into their jobs today. So they'll be going into a little bit more about that. What else? We have about 70 teams each year that compete in our APAC, HPCAIC competition, so that's always kind of nice. So we try to hit worldwide as we can. The Student Cluster Competition in ISC, we try to get a lot of regions involved too. We're expanding that to about 10 teams. Usually we've been in between 5 and 7 since COVID. So now we're able to expand that one out a little bit more. And then we have a graduate student series at Stanford that's an accredited course. Which is always nice because we get some pretty luminary speakers that kind of come in for that. And then there's conferences like this that we do worldwide, all free, all available online. So if you can't make it, we have all the material there for you. We try to hit every quarter. Summer we used to have an event, but I think we just enjoyed the vacation a little bit more. So we're just going to just relax with that for the time being. Glad you're here. Hope you have a great 2 days. And of course, for more information, you could just visit our website. So, I'd like to bring up Mark Wilkinson. We'll be going over his slides.
Thanks, Brian. So, I'm Mark Wilkinson. I'm director of the DiRAC HPC facility, and I'm a professor of astrophysics here at Leicester. And it's a huge pleasure to welcome you all here today, both the people in the room and the people online. We've been holding this conference in the UK since 2019. So when we started out, we had about 50 or 60 people. This year we're up to about 150 people registered, and so over 120 physically here and a good crowd online. Encourage people to register. If they haven't already registered, the online registration is still open. So if people want to join, if you mention it on LinkedIn and whatever, people can still join. So I realised I never talk about Leicester in any of these presentations, so I thought for a change today I'll show a slide or two about Leicester, because I think not everybody will have been here before. So the University of Leicester was founded in 1921, and 2025 is actually the centenary of the first physics student, so that's coming up next year. There'll be events to celebrate that. It's the only university in the world that's a living memorial to those who died in the First World War, and it was crowdfunded by the people of Leicester. So it's actually, in terms of the theme of the conference about democratizing access to things, it's a nice example of that. And the motto is Ut vitam habeant, that they may have life, and so that's kind of reminding us that the kind of inspiration that the university is built on. It's been a very good year. We were rated gold in the TEF in 2023. We're the Daily Mail University of the Year 2025, and we're shortlisted for the Times Higher Education University of the Year, so that'll be announced shortly. That's all I'm going to say about Leicester. I'm going to talk about some work very briefly that's going on here in Leicester in the computer science, the informatics department, and it's work that Ashik Anjum and I are doing on AI, combining AI and simulations in cosmology. Now, when I say Ashik and I are doing it, I'm not doing anything at all. The people who are doing all the work are the other names that are here. So there's Craig Barr, Corentin Uper, Azam Khan, Shiki Su, my student, and Aliza here. So if you guys could all put your hands up so that people can see you, okay? Go and talk to them if you'd like more information about any of the next few slides. So I'll go quite quickly because I just want to give a very brief overview, and I'm already abusing my right of in the welcome talk to say this. So what the problem is, cosmology simulations, there's 15 orders of magnitude in terms of temporal and spatial resolution. And so what we're trying to do is include as much physics as we can in as realistic a way as possible. So what you see in this image is a simulation of a chunk of the universe. And when you zoom in on it, there's lots of substructures. And so one of the substructures, if you look at the up in the top there, that substructure, just to give you a sense of scale, is the entire Milky Way. And so what we're trying to do is simulate all the things that go on inside galaxies, but in the context of a much larger hydrodynamic simulation. And so that's very challenging, obviously. So the first piece of work I'll talk about is called Deep OJET, and this is using a deep operator network to scale the resolution of simulations up and down. Now, deep operator networks, as you may know, they're trained to learn operators. That's mappings between input functions and output functions. And in this case, we've got two networks, one for the variables of the problem and one for the coordinate system of the problem. And they're in two fully connected networks. And the reason when you do that, it means that you can change the resolution and the geometry of the mesh that you output the simulation on. And you can do that either increasing the resolution or decreasing it. So what you see in the center is an output from a simulation done at a resolution of 32 by 32. Doesn't matter what that means, but that just sets the scale. And it's actually the center of a galaxy with two jets of high energy particles coming out. Now, in the upper two panels, that's from the prediction from the network as if you had run the simulation at twice the resolution. And similarly here, this is what it actually would have looked like. So that's the output of the numerical version. Down below, it's if you had done it at half the resolution. And again, that's the prediction, that's the actual snapshot. And the thing is, what you see here is it's capturing, this is very preliminary work, it's about 10 days old, so there's refinements to be done, but it's capturing the basic structure of what's going on in the simulation. And what's really neat is in this one, there are features in here which are not in the actual numerical one. That's a positive thing, because what's happened here is this low resolution version includes physics that's only in this higher resolution version, but it's giving it what it would look like in low resolution. So it actually means you can now have a very efficient way of producing examples of what the output would look like that you can then feed into much larger simulations. On a slightly different scale, Shiki, my student, is working on radiative transfer, and this is again trying to study the interaction between radiation and matter, in this case around a star. And so what you see, the equations are here that she's modeling, and again it's using a 3D ResNet to actually do the AI side of it. So on the top you've got the output again of numerical hydrodynamic simulations looking at the gas structure around a binary star, and at the bottom you have the output of the neural network. So the thing is, as you can see, the general features are very well reproduced, but the thing that's really cool is that if you look at some of the specifics, that these are at 3 different frequencies. It's as if you observed it at 3 different frequencies, but it's 3 different images. It doesn't matter. And what you see is this region here is qualitatively very different as you go into the different as you go to different frequencies, and that's reproduced in the output of the network. So again, this is work in progress, but it shows it's the use of these AI techniques to feed into our numerical simulations is becoming really important and valuable. And the final thing I'll mention today is looking at energy-aware scheduling. And so this is work being done by Aliza here. And so the idea is we measure the energy consumption of systems when they're running particular workflows, and then we build a neural network model of that energy consumption. We then can generate some data, artificial data, which we can use for both to study what would happen if we changed settings in the system, like what the scheduler policy was, and we can do uncertainty quantification by comparing the data that we generated with actual measurements on the system. So the idea being that you end up with a digital twin of your computer cluster, which can be optimized in terms of energy based on the scheduler you use. And so examples of the impact of that are here. So you've got 5 different blocks each of which is associated with a different workflow. These are all workflows from the Large Hadron Collider data processing. The different bar colors are different policies for the scheduler. And so the point to take away from it is this is energy consumption here. So you do get significant differences depending on what your scheduler policy is in terms of energy consumption. Now, obviously that has an impact on throughput for the jobs. So you end up with kind of conclusions like this, that you can clock down for one of the workflows, this one here, you can clock it down, the system down by 15%, change the scheduler policy, that will save you 10% of your energy budget, and it'll just have a hit of turnaround time of 5%. So again, this is work that we're going to look at applying on some of the DiRAC systems next, and look at the workflows that we're dealing with. So I'll finish there. This slide is the slide I'll show at the end of tomorrow. I'm showing it here today because not everybody will be here tomorrow. These are all the people who need to be thanked for all the work they've done. Brian implied that I had done something to do with this conference. I've really done genuinely nothing apart from having a few meetings. All the work's been done by Brian and Gabby and Lisa. So thank you to them. Thank you to our sponsors. As Brian said, please talk to the sponsors. They have booths downstairs. When you get your coffee, you'll be encouraged to go into the room with the sponsors. Please take the opportunity to do that. Okay, I'll leave it there. Thanks all for coming. Have a great couple of days. And I'm going to now introduce Paul Calleja from Cambridge, who will give our opening keynote. Thank you very much.
PA let me sleep later today, which is dangerous. Hi everyone, I think most of you probably know me. I'm Paul Calleja, I'm Director of Research Computing at the University of Cambridge. I'm going to give basically the same talk I always give, sorry if you've seen it 10 times already. I'll probably stray off the track a little bit if you want. We can talk about many things. Let's not go there. Okay, so today I'm going to talk about the service, AI and simulation service we run, how we try to really use this to drive innovation across research, industry and government, and that's actually much harder than it sounds. It's getting old really sucks. I can either see my slides or you. I'll flip between the two. So over the next 30 minutes we're going to just have an overview of our AI and simulation capabilities that we provide. We'll talk a little bit about the Innovation Lab, which is an industry-funded activity. And I'll try to finish on a question. If I don't talk at you for too long, really, how can we do better at driving innovation? Yeah, that kind of innovation life cycle is a tricky thing. And I think most of the time we just provide resources to people that know how to use them, who do the same thing they've always been doing. And the innovation part is kind of left at the end with the money you have left over after you've done what you've been doing for the last 30 years. I think AI is going to change this because it's quite radical. And new processes like what Mark just described, for example, can be really revolutionary. But how do we focus on doing things differently instead of doing things the way we've been doing them for a long time? Yeah. So just some key characteristics of the service. So we've been running for 18 years now in Cambridge. That's kind of scary. I did not have this 18 years ago. And my son who's sitting at the back was only 2. Which is kind of weird. Hiring is so annoying, it's quicker to grow them than hire them. So, 18 years ago we had 80 users, relatively small, parochial university service. Now we've changed a lot. We're kind of a major UK AI and simulation service provider. We've got 3,500 users now from a very broad range of disciplines. This is one of the things that I think that characterises the Cambridge service. We're very pan-discipline. Which means our user support and RSC capability is reasonably broad. And I did some analysis of the top 500 for a grant proposal that was not successful, but anyway, I did the analysis. And it looks like we've provided around 50% of the UK top 500 performance over the last 7 years, which is actually quite interesting. We have not soaked up 48% of the money. I don't know, you can read what you want from that. And our model is slightly nuanced from other centres. We're a multi-stakeholder centre, so we have stakeholders from a broad range of funding council activities. So STFC DiRAC is a major stakeholder, STFC IRIS, EPSOC Tier 2, STFC SKA work is done on our machine. Actually, our largest funder at the moment is HPCAIC, the Atomic Energy Authority, Column, that's responsible for fusion research, and recently we're a new UKRI DSIT air service provider. I'll talk about that later. And so what we do with all those different funders is we pool their money, and of course the money comes in at different times. We pool the money and we do kind of incremental, kind of stepwise upgrades of a system that we keep kind of taking stuff off one end and putting stuff on the other. And this is quite interesting. So we have a shared multi-stakeholder service, which gives us economies of scale and various other advantages to our stakeholders who basically swap resources amongst themselves. Other characteristics of Cambridge is we have a strong in-house technology team. We invest quite a lot of resources in technical staff. We do our own system design, system implementation, system support, obviously user support. So we don't buy a system from a vendor and then have the vendor deliver it and support it. We buy components from a vendor. We fashion a supercomputer out of those components and support it ourselves. Obviously, you need an economy of scale to be able to do that. But once you have that economy of scale, I think it gives you best fit between science, need, and technology deployed. You have stronger value for money, agility, and I think it lowers the risk because we don't rely on the contract to threaten our vendor if things go wrong, because that rarely works. Vendors are normally better at the suing game than we are. And so you own that risk, you share that risk with your vendor, and I think that lowers the overall risk profile of the activity. We do have a strong commercial partnership model. We use that for driving revenue from partnerships with supply chain. Obviously, we use that for technology development, and I think it helps with our overall impact story quite a lot. We do have a focus on innovation by co-design. I have some slides on that later. That's in the Zettascale lab. And obviously all of our development should be driven by scientific need, not lab director ego. Although my ego does slip in occasionally. We try to get rid of it where possible. But you know HPC directors, you know them. Okay, Sadaf, ego and things. Let's not go there. Mark's the only one that doesn't have one. It's very nice. Yeah, I think it comes with. You think it comes with age? Is that where it comes from?
Age has nothing to do.
No, it's born in you. I find Mark was just born nice. One of the few nice ones. What else do we do? Oh yeah, we have a quite an active collaboration model with Africa. We've done a lot of work in Africa for the last 17 years now. And we support 2 large systems in Africa, one right down in the south, in Cape Town with CHPC. I've been helping Happy build and run his systems for 17 years now. And our latest partner in Africa is UM6P in Morocco. In fact, that's the largest HPC system on the African continent. That's a Dell Intel system. And we designed that, implemented it during COVID, and run that as a managed service completely remotely for that university. So, just some facts and figures. 90% of our activity is external faced national services, 10% of our activity is internal, so we're kind of swept from being 100% internal to only 10% internal over the last 18 years. It's much easier to get money outside of Cambridge than inside Cambridge. So I just follow the money. We talked about our development work. We have around £100 million of equipment in operation at the moment. None of that is more than 4 years old. We have 40 staff, should be rising to 55 or 60 over the next year with some new activities. We have 1.8 megawatts of power and cooling when the DC is working correctly. It's not at the moment. We have issues with our cooling system caused by negligence. But that will be dealt with hopefully this year. Water's really tricky. Water in your data center, you need a non-negligent estates department if you're going to have water. We have 30 petaflops of double precision Limpac spread out across a whole load of different assets, around 3,000 servers from Dell, 45 petabytes of storage, mostly spinning disk cluster, some tape, some solid state, which we'll talk about. And we're ISO 27001 compliant. We put a lot of time and effort into building a trusted research environment based on these ISO controls, and that really enables us to do a lot of work with clinical medicine and government on sovereign data sets. Super. So our innovation activity is concentrated in something called the Zettascale Lab. It's an awful name. I'm going to rebrand it. I think Zettascale was a busted flush. Exascale was almost a busted flush, but Zettascale certainly is. We're never going to get there in my lifetime, I don't think. So we have around $10 million of funding. That's coming to the end now of that first 4-year funding program. I think it's going to renew at least for another 2 years. We do 2-year funding rounds. And really, what does the Zettascale Lab do? Talk about on this slide. So really, we try to kind of foster this innovation co-design cycle. And maybe you can be thinking about this for questions and discussion at the end if I talk quicker. There are a fusion here, really, of science use cases, kind of service provider and supply chain inputs. So we create this kind of melting pot, this critical mass of use cases, skills, and infrastructure, test beds, not production. And then we try to drive science-led technology development. We build a platform that we think will give an advantage. And then we kind of test that and iterate around in that loop. There's a whole load of themes. We try to have thematics that we work on, of kind of pain points, although a lot of these pain points really are from a service provider perspective. I think we should probably turn that around and make them more user-led. You can see this is very kind of service provider focused in a way. So energy efficiency is a thing. We spent a lot of time looking at various strategies for energy efficiency. Mark talked about frequency control. There are loads of different strategies. I've got a slide on this later. One API is a programming environment from Intel that allows you to have cross-platform code portability, especially useful with GPUs. We do a lot of work on that. I have one slide on that later. A big push on trying to modernize in our research computing middleware environment, because a lot of us are using technologies and methods developed in the DOE 30 years ago. It's time to get rid of them and do different things and move to a more cloud native type environment. The world has moved on. Most HPC centers have not. We need to look at that. I have some slides on that. Storage is obviously a huge issue in old-fashioned HPC, where we were looking at bandwidths mainly, big bulk bandwidth transfers. This has changed with AI, and we're now looking at a different kind of pain point in IOPS. And so we're looking at various strategies there with solid-state storage and how you use that in a transparent way. Again, it's more difficult than you would think. We're looking at how one moves from an HPC, traditional HPC, kind of Slurm batch scheduling environment. How do you make those systems more cloud-like for AI users that are used to running in a cloud? There's a lot of orthogonalities between old-fashioned HPC and modern cloud and AI. And Salef and I talk about this a lot. Salef is actually really useful in these discussions, so go and talk to her about it. She knows more about it than me. You're talking about this, right, I guess? Yeah. I'll leave all that to you for your talk. We work together in AIR, and we have a lot of development activities here. I'm going to speed up because I'm going to run out of time. You've got the slides. So energy efficiency, because where does it hide? Where should you look? And if you look end to end across your whole data center kind of activity, there's some interesting things to look at. So I tried to list some things that you can change. And so, for example, most of us traditional old-fashioned data centers will have air crack units with traditional fridges outside, DX. You could deploy water to the back door with adiabatic chillers. You could go one step further and put DLC. Of course, on the compute, you can use CPUs, you can use GPUs. They can be old generation, or you can switch to the latest generation. And then there are things you can do operationally. And what kind of savings do we get here? So I tried to quantify it from looking at things we've done in Cambridge. Actually, when I wrote this slide, it was actually quite surprising. So just moving from old-fashioned DX crack units to water-cooled back doors, chilled by adiabatic coolers, saves you 40% energy just in that one data center infrastructure change. If you move to DLC on the servers, so you put the water now inside and get rid of those fans, that saves you another 20%. I was shocked to see that if you take a modern 8-way GPU server and you cool it with air, that 6U 8-way air-cooled GPU server, the fans are sucking 2 kilowatts. 2 kilowatts. Just for moving the air. That's crazy. So you get rid of those fans, 20%. It's about 20%. If you can move your workload to GPUs, with some recent analysis we've done with our Intel Ponte Vecchio chips, some work the UKA did, and you compare that to a modern, same age CPU, it runs 300% more energy efficient. Yeah. So, but I'll estimate for this calculation that you can only use that on 50% of your workload. Okay. We could argue about that. It's just a number. Again, if you move to the latest generation of GPU or CPU from the previous generation, you normally get a 30% kicker for power, normally. Yeah. If you do frequency scaling, like Mark suggested, you can get up to 20% power drop. Yeah, now energy to solution might be different, but I've just put power here. This is rough. Code optimization, yeah, pick a number. I just said 20% of low-hanging fruit. All that nasty grad code that you might be able to improve. Jeremy did some analysis on this, you remember, like 20 years ago. You add all those up, and it comes to 330%. Oh, and heat reuse. So if you can take the heat out and reuse it in some municipal, it's normally about 50% efficient. Yeah. So that's 330% you can gain by doing these things. On my energy bill in Cambridge, that would save me $1.5 million a year. Actually, I probably wouldn't bank that saving. I'd just squeeze more computer power into my power box because I've run out of power. So you can either bank the money or just buy more computers and not have to build a new data center. Yeah, so I thought that's quite interesting to look at where to go. And obviously the biggest savings is just get rid of your old aircon and replace it with water. So I talked about the One API. We do a lot of outreach and training and SQL courses. If anyone's interested in that, just reach out to me. We can do hackathons and things with SQL. I know, I'm good. That's where I should be. So, middleware. Obviously, we know traditionally we had a different kind of software stack for different functions. We can change that now. We have a big push with OpenStack. We've been developing OpenStack for research computing for the last 8 years in close collaboration with a UK SME called Stack HPC, run by John Taylor, Stig Telfer, John Garbett. Here we kind of use OpenStack to create a kind of a shared configurable hardware base, which we control with OpenStack APIs in a modern way. And then with Ansible, we can create software-defined research platforms on top of that infrastructure. We bolt our DevOps toolkit onto that, which enables us to run our service in a much more kind of DevOps-orientated fashion, which is revolutionary with the way you run your HPC center. And this becomes quite a powerful way of running. We call that the scientific OpenStack. We have funding from UKRI, various pots of money from UKRI to kind of develop this and create a community project around this with documentation, a repository, and assistance in getting that running. It's gaining traction on big sites. Of course, there is an overhead for running OpenStack in terms of complexity. Companies like Stack HPC can help with that complexity because you can just outsource that to them. We have a long-standing support contract with them to help with that. And it's a really interesting way of running your HPC. The flexibility you get and the things you can do in this environment are really quite amazing compared to how we used to do things. Another project in the lab is we've got a big observability project run by Dominic, really collecting a whole lot of metrics and logs and traces and quite a kind of complex software tool chain that he's created to collect those metrics, to analyze them, to store them and make them available through various dashboards that we can make kind of on demand. This is kind of cool. This is all available on our Git repository. Just to touch on storage, this is quite an old slide. Don't look at the detail. It's really just meant to show pools of different compute nodes. Over here, we'll hang off of an InfiniBand network, and then we hang off various solid-state storage test beds. They're not production. These are all funded by Excalibur. Normally, when we buy things, it has to go into production, and users want to use it, and you can't mess with it. These were just purely for messing with. And that's allowed us to test all kinds of different file systems and ways of making those file systems available. We've just re-implemented the Slurm burst buffer code because we found it had some really nasty security issues in it. We've re-implemented that now. Okay, let's not argue about burst buffers. I can see Sadaf's face from here. Yeah, I agree with you, but it's just a way. Burst buffers are kind of have problems, but we need to work out how do we make large NVMe resources available in a transparent way. And this is an ongoing project. If people want to come and talk to us about this, we're going to be standing up a large solid-state file system for our Air machine, and we're still debating what the best way to make that available to users is. These are non-obvious issues. So this is Dawn. This is part of the UKRI DSIT Air AI resource system. I'll skip this because I'm sure you're going to talk about Air, aren't you? A little bit. Currently, this is the fastest AI system in the UK until South Africa gets a machine working sometime soon. We've had this in operation for a year now. One thing we are working on with our Air machine and Sadaf's Air machine, we're using some technology from a company called Wardour to create a single pane of glass federated across those two systems. Again, Sadaf may talk about that. I know, it's good. I can speed up. So this is what Dawn actually is. It's 256 Dell 9640 servers, 2 CPUs, 4 GPUs. Each one of those servers has 4 HDR200 NICs in it. It's water cooled. We had to do a lot of additional hassle in our data center. A very large internal manifold, looks like a dairy. Cost £1 million worth of pipe work. We had 4 pipe fitters with blowtorches and pipe benders in our machine room for 4 months, creating this bespoke water cooling system. Because it pushes 240 litres a second of flow through those servers. Look at that thing of beauty. I could just look at that all day. That is the core switch for this system. I think it's 34 kilometers of fiber cables, 3,000 connections. It's very well interconnected, probably overly so, but we can test how much interconnection do you need. Yeah, Intel paid, it's all good, don't worry. No taxpayers' money was wasted on this system. So we are in early science mode. We started in Feb this year. So we've got users on the system to help us understand what AI users really need, and waiting for DSIT to be ready for launching the service. Also, we have to stabilize the system because it's new. So there's 140 users, 65 different projects. We've been surprised actually how easy it is to move AI codes from NVIDIA to an Intel, much easier than simulation codes because it's just a library called PyTorch which is ported, and performance is okay, and it kind of works. And most users don't really care about if it's 10% slower than it should be if you've got lots of GPUs there and the queue's short. That's all they care about. We had a Pioneer Day last week talking about Dawn, and the most common feedback was it's great because the queue's small. Users are easy to please. I won't go through the projects, there's lots, but actually the one thing I will say on projects is we're seeing a lot of projects like Mark spoke about where you're kind of using AI in a simulation workflow in materials, in fluids, in cosmology. This is becoming really, surprisingly quickly, quite mainstream, because just a year ago when we were here, it was all new. So you really had that guy from the States talking. Now people are just using it, not developing it, which is really interesting because this is giving 100x, 1000x speed up, so you can be seeing kind of exascale performance on a petascale machine, which is quite revolutionary, I believe. And the impact of this is going to be huge in how we think about what machines we need, how we think about how we provide machines. It's going to change things radically, in my opinion. I'm going to speed up. Now, this is what we did with HPCAIC, looking at a simulation code. It's not all AI. It's a GPU, of course. It does simulations also. This is a Monte Carlo simulation for fusion. And it shows basically a 11, 12 times speed up from a contemporary GPU to a contemporary CPU, and the power only goes up by 3.5. Performance goes up 12. That's why you use GPUs for simulation. So last slide. Yeah, perfect. So, and I'd be interested to talk to you about this in coffee and things. So how do we really drive innovation? Okay, how do we take these technologies and help users do new things with them? And users that haven't really done HPC or AI before are the really difficult ones. Some kind of learnings that I think I've found is it's easier to scale across communities of practice. So if you have communities of practice like DiRAC, for example, I think one of the reasons why DiRAC is successful is it's a community of practice really on quite a restricted set of disciplines, and learnings and things you do in one kind of carry over. So this kind of like domain-focused or mission-led kind of activities I think are interesting. DiRAC's been doing that kind of quietly for a long time, but we don't really talk about those facets that make it successful. So if you innovate within a community of practice, it's easy to scale that innovation across. So you kind of innovate once and share. And of course, why you have to do that is this innovation is really labour intensive, and we just don't get funding for that. We get funding for standing up machines and doing the normal boring things, but not helping users do new things. That's quite difficult. Of course, AI makes this problem worse, because it's new things and things that most people don't really understand because they tend to black box it. So that tends to be difficult. Yes, it'll be interesting to get people's views. Of course, when you go out of academia and you move into industry, it gets even worse because it's more siloed. So industry is siloed. And I've been working quite a lot in government the last year and a bit, and I was shocked, maybe I shouldn't have been, at how siloed government is. So one department doesn't talk to another one at all. So we've had people down from HMRC, the next day you have people in from DWP, they have similar problems and they're completely siloed. So how you do kind of sharing and innovation across government where you learn once and share is actually quite interesting. Of course, industry is ultimately very siloed. So instead of asking me questions, we could discuss this. I'll probably run out of time. We can discuss it in coffee, because I think as we move forward with developments in our DRI in the UK, I think government will be wanting to focus on this element, not just give us money to build large hunks of tin, which we should probably be running in the cloud anyway. It's how do we actually innovate with this infrastructure. And that's it.
Thanks, Paul. So we have time for one quick question. Is there any online, first of all? Yep, okay. That's all hand there. Yeah, James.
Hey, James.
Hi, Paul. I should have said, please wait for the microphone.
Hello. So, Paul, part of the amazing success you've had in Cambridge has been the way you've built those relationships with partners like the Intel relationship and so on. In some of our institutions, that's more difficult because the expectations of the institution is, every single purchase is its own best competition. It's quite hard to build those sense of partnership. Can you advise on how you've managed to get the institution to approve the sort of partnership flavoured approach into your industry relationships?
Yeah, well, actually, all of our procurements are competitive and have been won in an open and fair way. But we have moved towards framework agreements. Yeah, and this is really helpful. So instead of running a separate procurement for everything we do, we have a long-lived framework. The framework is let competitively. A vendor partnership will win that framework, and then we call down off of a framework. This is really actually necessary because of the way we're given money in the UK, which is obviously not strategically or planned. It's back of the sofa money that becomes available at Christmas and has to be spent by March. You can't do that by competitive procurements, and so a framework really works. Yeah, so the framework was necessary to make us the spend of last resort, and that kind of works a lot of the time. But yeah, and in Cambridge, of course, they leave me alone. Cambridge has a habit of leaving academics alone. As long as you don't burn the university down or kill someone, you can get away with murder.
On that note, we should move
Thank you.